Hello, my name is Bill Howard. I'm the product line manager for vertical machining centers at Makino.
Hello, my name is Greg Pozo. I'm the team leader for applications for the vertical machining centers.
Today we'd like to present to you a webinar entitled 5XC, which stands for 5-axis continuous. During the webinar today you'll see a text box. If you'll have any questions, you can type into that text box and hit send, and those questions we'll be able to see those questions. We'll be looking at those questions during the webinar, and as time permits, at the end of the webinar, we'll address as many of those questions as possible. In addition, this webinar, within about a week or so, will be added to the archive at www.makino.com. There is a ton, there's just a lot of webinars out there, a lot of technical content. And like I said, if for some reason you get called away or you'd want to look at this again or share it with someone else, within about a week, this webinar will be at www.makino.com. Obviously, the first question is 5x continuous. What is it? In the past, years ago, basically everything was programmed based on 3 axes of a vertical machine tool, X, Y, and Z, and you ended up, as you can see, with long tool reaches and very difficult geometries and obviously less than optimal cutting conditions. Maybe 10 years or so ago started to be the advent of tilt and rotary tables. And what we could do then would be obviously position the 2 most inaccurate or the slowest of those axes. That's what the first 2 are. So your tilt and rotary you would position, and then you would color or machine the part using the X, Y, and Z, coloring the part in basically 3 axes. Well, now today we're here to talk to you about 5X continuous, or 5XC. What 5XC is the next logical Makino technology evolution for die and mold manufacturing productivity. 5X continuous is built on technology. I can remember as a child watching John F. Kennedy talking about by the end of the decade they wanted to put a man on the moon. Well, they didn't go out the next day and do that. Obviously, they had to develop the technology. The Mercury program, just basically the missile technology to do the lifting of the weight. And then you had from the Mercury program into the Gemini and then into the Apollo and all the technologies. Well, 5XC is like that on a number of fronts, not just machine tool, but tooling and programming, which Greg will talk to you here in a couple slides. Let's think about tilt trunnion table technology, and let's go back to the 2+3 days. Those, as far as positioning accuracy and repeatability, were 3 to 5 arc seconds. But more importantly, look at the speed. They were very, very slow. Well, it looks slow compared to what we can do today, 30 to 50 RPM. Today, we're going to use the D200Z as a machine to show the kind of technology and capabilities that are out there with the advent of DD motor technology. Obviously, that's a built-in technology or a technology advancement, but DD motors, which gives you speed, very, very good accuracy and precision, and it also eliminates lost motion. If you look at today's DD motor tables, tilt trunnion tables, you're looking at positioning of ±2. You're looking at repeatability for the tilt of ±2, and on the rotary of ±1. So the accuracy is significantly tighter than what we had back in the 2+3 days. And the other thing is you're looking at anywhere from 100 to 150 RPM. So if you look back at where we were at 30 to 50, 100 to 150 is significant increase in productivity relative to where we were just 5, maybe 10 years ago. So we've seen dramatic increases in productivity, precision, and performance in the basic technology available in the machine tool itself. Let's take a look at machine motion as well. Talk about servo feedback. Makino has always tuned for performance, but today, with the next generation servo motors, we can actually, there's a much tighter control, much more responsive and tighter servo tuning. You can see the noise on the one slide versus the noise that are generated in today's technology. So that allows us to tune and improves feed and smoothness by 3 times what we've had in past generations of motors. Let's talk about core cooling and ball screws and bearings. We use a core cooled system where we're cooling the bearings and also core cooling the ball screw itself. So that gives us precision. And the other thing about cooling is it reduces the temperature, so it improves the longevity and performance of the machine tool. Another thing is performance itself. Let's talk about the D200Z again. Look at the speeds there. You're looking at 60 meters a minute, X, Y, and Z. That's 2,400 inches a minute. Well, I can remember when those speeds were down in the 500, 600, 787 inches a minute. The other thing about it is not only the speed, but look at the time it takes, or the G rating for X, Y, and Z here. We're looking at 1.5 Gs on X and Y and 2 Gs on Z. So it gets from dead stop to full speed very quickly. So it's very responsive. You look back again at the 787 inches a minute and 0.4 Gs compared to the technology available in the market and machine tools today, and particularly the D200Z, and it's dramatic. Not to mention precision. That D200Z we're using as the example has 0.0125 micron scales. So not only is it quick, it's extremely accurate as well. Again, dramatic increases in productivity, precision, and performance. Along with the advancing technologies have been advances in control motion technology. Makino has had what we call super geometric intelligence, SGI 3, SGI 4. We're now on SGI 5. And if you're familiar with that at all, obviously it's using point-to-point and more points to allow us to run smaller and smaller block lengths, so therefore we can carry higher and higher velocities through complex contoured 3D shapes that are typical of die and mold and medical type applications. What we've done with that technology is each succeeding generation has driven the cycle time further and further towards the absolute minimum cycle time given the geometry that you have. You get into 3D contoured surface smoothing, 3D and 5-axis smoothing. Those are all enhancements to the basic super geometric intelligence technology. VP control is also a development here recently, particularly in the 5-axis market. What we're doing in VP control is you realize that as you tilt and rotate, there are minute little errors, and in order to get the most tight volumetric accuracy, what we do is we'll go in and actually measure X, Y, Z tilt rotary axes and do an error table or an error plot, which gives us an error map, which you can kind of see there on the right-hand side in the center. And then as we're machining and contouring in 3D, 4D, 5D, or 5-axis continuous, we can use that error map to actually compensate and provide an extremely accurate, extremely tight workpiece. Inertial active control, a lot of people don't even think of this, but if you think about tilting and rotating a workpiece, as you tilt and rotate, there is an inertia. And that inertia, given the weight and the speed, can actually impact the accuracies. So Makino has a proprietary development, as VP control and super geometric was, in order to take into consideration inertial active control and that impact on error as we take both the weight or mass of the workpiece and the speed into consideration. Another thing to consider is the advances that have come along in just programming systems for the control in 5-axis. Things like TCP or Tool Center Point Control, tilted work plane have made it easier and much more accurate in order to program, in order to do 5-axis work on the machine tool. Finally, we've come up with some things ourselves we refer to as preparation for high accuracy. We talked earlier about tuning. We can actually go into a tuning cycle. We can trigger a tuning cycle on the machine tool and go in and check specifically to get tighter control over quadrant crossover points for better surface finishes and better tolerancing. We can also go into the inertial active control, or IAC, and basically tune that. Finally, there's center of axis rotation as well. We can go in and use a spindle probe and go in and check back for the tilt and rotary axis and recalibrate and check the center of axis rotation, because that value is very critical for your tool center point control and your tilted work plane. So again, higher speeds, higher efficiencies, higher precision, higher performance, all built on technology. Along with that comes technology to make the machine more user-friendly. Makino has come out with the latest generation Professional 6 control. What that control aims to do is to streamline and make it more easy and more efficient, and it's based on a workflow approach to getting the machine into production. So basically from a dead stop to get the programs and the tools and everything into the machine and get producing for a very efficient workflow. It speeds up the setup and the data management and getting started, so therefore it increases the productivity of the machine tool. It also incorporates a bunch of GUI or graphic user interface for ATLM, which is tool measurement, and AWMS, or automatic work measuring system. And it's targeting productivity. We want the machine to be as productive. We want the spindle to be busy all the time. Another thing is, with 5-axis technology, you run into situations where you'll actually be cutting and you'll move the workpiece relative to XYZ using the tilt and rotary, and you'll find that the workpiece is now in positions where it never was before. So it's very important to protect the investment by using, again, a proprietary feature that's been developed called Collision Safeguard. Collision Safeguard uses all the data that's been input from the program. There's a model of the machine tool in there. You need to input a model of the workpiece, model of the tooling, and it will be running in the background live and can anticipate and prevent you from having collisions on the machine. So you're protecting the investment of the machine tool. Finally, it's user-friendly. It's very effective for data management, very productive, and actually can be kind of fun. Greg, I'm going to ask you to talk now a little bit about some of the driving technologies.
Great, thank you, Bill. So one of the driving technologies towards 5XC is the advancements in tooling technologies. And one of those advancements is the multi-flute or 6-flute end mills that have come out to the market recently. Some of the advantages of using this type of tooling is we're able to fully utilize all the multiple flutes. So what that basically does is allows us to maintain higher speeds and higher feeds because we have more flutes per cutter. It also gives us more cutting surface on a given tool. So with that, we will get longer tool life because there are more flutes or more area on the tool that is being used for cutter. So that gives you longer tool life, higher productivity, better surface finishes at lower cost. Another technology for tooling that has come out is the barrel-shaped tools. What this barrel-shaped tool is basically it's a large radius tool with a small diameter on the same tool. The advantage of this unique shape gives you the ability to maintain surface finish at a given factor with fewer steps. Because of the larger radius on the tool, we're actually able to increase the step over and yet maintain that surface finish. With the combination of the smaller radius on the tool, it also allows us to get into the tighter corners of the model that the larger radius cannot. Because there's the larger and smaller radius on that tool, that helps us to machine one continuous surface and reduce any kind of blending issues, because the larger radius can maintain the open areas of the part, and because of the smaller radius on the tip of the tool, we can actually go into the corners and machine those areas with one tool instead of having to change them out and try to match the blending. With the barrel-shaped tools, we also have multi-flute technology in it, again giving us higher speeds, higher feeds. With that, it gives us longer tool life, higher productivity, better surface finish at a lower cost. One of the advantages of 5-axis continuous is also the ability to target the ideal contact point of the tool for the best cutting condition. As you can see on the picture on the left, you basically are trying to cut with the tip of the tool in this scenario, where there really isn't any velocity and it's more of a chiseling action, and you don't get good clean cutting of the tool. The picture on the right, where we've actually tipped the tool, we're maintaining it to a larger portion of the diameter and using a better portion of the tool to get good cutting conditions. With 5XC, you're able to maintain this good cutting condition by the control of the tool axis. One of the other supporting technologies for 5XC is the cam systems. The cam systems have evolved over the years, and previously in the past they were one of the bottlenecks because of the complexity of actually trying to program in 5-axis. So with the newer cam systems, they've added new features that help support easier programming in 5-axis. In this particular scenario, we're taking a look at a cam system with a standard 3-axis tool path. This one happens to be an optimized constant Z. What a lot of the cam systems are doing now is combining the 5-axis technology with their standard 3-axis tool paths. This allows the programmers to use their standard 3-axis tool paths and then just add on the new tool axis capabilities to make sure that you're tipping away from the tool and avoiding collisions. You have automatic features where we can actually lead and lean the tool away based on a holder or clearance condition, helping to allow the system to automatically make that tip for you instead of using complex 5-axis geometry to support the tool axis control. Cam systems have also evolved in regards to supporting the new tooling technologies that I spoke of previously, the multi-flute end mills and the barrel-shaped tools. Most cam systems now have a dialog box to program or put the values in for the barrel-shaped tools with the smaller radiuses at the tip and the larger radiuses on the outside. With these combination of supporting the new tooling technology and the adding on of the multi-axis tool paths, we can help program in 5XC to reduce the number of tool paths. Since we don't have to go back with longer tools to reach into areas, we can now just tip the tool axis away, avoiding collisions, using one single tool path. This in turn is going to help reduce blending and matching stitching of the shapes of our parts. One of the challenges when you get into doing 5-axis is the fact that we are now adding on 2 additional axes, and we can be either moving the spindle around the part, or we can actually be moving the part around inside of the machine envelope. What this does is it gives us additional things to consider for collisions. So one of the things that we would recommend is always having a collision software to check for these components. One of these is called Vericut. Now, Vericut can do a very good job of checking this in a virtual world, but when it actually comes to running on the machine, there are additional components that Vericut does not know about. A couple of those are the actual tool length and the actual location of the part on the machine. With our new collision safeguard technology, we can actually take the information from a Vericut session and put it on the machine where it can be running prior to the actual machine motion to let the operator know of any kind of conditions where it could potentially collide. To support this, many CAN systems have a Vericut interface where you can directly take the information from the CAM system, streamline the process a little bit, and take that and put it directly into the machine control to give you some of the benefits of protecting your machine investment. These benefits are significantly reducing the cycle time, reduction of the setup and handling of the part, increased throughput and reduction in lead times, higher productivity, improved access to the part geometry, reduction in the number of tool paths to be programmed, more uniform surface finish and quality, increase in tool life, better blending, matching of the stitching of the tool paths together, reduced hand finishing, use of less expensive tooling, lower cost, and increased profitability. In this particular example, we're going to talk about a graphite electrode which has a honeycomb shape that's used primarily for speaker molds in the automotive industry. I am now going to turn this over to Bill Howard to continue.
What I've done here is I've taken the information from that honeycomb graphite electrode and broke it down into the different tool paths and everything. And so you see the 3-axis approach here, and then here's the 5XC or 5-axis, full 5-axis approach. If we wanted to compare those, the first thing you look at is the cycle time. And basically the 3-axis approach, we're at almost 5 hours, 4 hours, 57:43, versus the 5XC is 4:03, so just over 4 hours. So that's about a little over an 18% reduction in the actual cycle time to make the graphite electrode. Second thing to look at is tools. If you look at the 3-axis approach, there's 4 tools there, versus the 5XC approach, there's 3. So obviously there's less tools, there's less investment in tooling, there's less tools to set up, less tools to get onto the machine. The other thing you look is the tooling cost. The tooling cost in the 3-axis approach was just about $60, $59.99. The 5XC approach was $23.43. I said $23.50. So you're looking at a 61% reduction in the actual cost of the tooling. Reduce lead time, obviously, by about a little over 18%. As far as machining cost, if we wanted to get an idea of what that part would cost, let's just say at $100 an hour, we're looking at $496 versus $406. So that's about an 18.1% reduction. That's obviously reflecting the reduction in the cycle time. And obviously that's money in your pocket. The other thing to keep in mind that an electrode is a raw material, or it's a cost that you need to go over onto the sinking machine in order, so you've reduced your cost in the overall process as well, in addition to reducing your lead time. What I did here was go in and took a look at the total part cost, where I've got the machining cost, as you can see there, 3-axis versus 5-axis, and the tooling cost. So we're looking at $556 versus $429.50 at $100 an hour. So there's a difference there of $126.50 per part. So on a cost basis, we've taken almost 23% of the cost out of that graphite electrode. I'm going to turn it back over to Greg now. He's got a couple more examples on lifters we're going to look at.
Thank you, Bill. In this particular video, we're showing 2 of the different operations performed on this lifter part. In the first example, we're showing machining in 4-axis motion, where we have a feed rate of 1,500 millimeters per minute and a pick of 0.15 millimeters. This is going to give us a cycle time of 59 minutes. We're going to take the same operation, but we're going to use a multi-flute or 6-flute ball nose end mill on it at a feed rate of 4,500 millimeters per minute, at a same pick rate, but a machining time of 26 minutes. In the last example, we're using full 5-axis with a barrel tool at 3,000 millimeters per minute, 2 times the original, and a larger pick rate of 0.45 millimeters with a cycle time of 13 minutes. In the next operation, we're machining the top of the lifter. In the first example, we're using a feed rate of 1,000 millimeters per minute, a pick rate of 0.105 millimeters, using a 2-flute end mill with a cycle time of 28 minutes. In our second example, we're going to use a 6-flute end mill at 3,000 millimeters per minute 3 times and the same pick rate, but a machining time of 10 minutes. In the last example, we're using the barrel tool at 2,000 millimeters per minute, 0.21 millimeter pick rate, and we're going to have a machining time of 8 minutes.
What I've done is taken the mold lifter statistics from the videos and I put them together in a little chart here. You'll see the first one where we ran it with a 2-flute 1,500 millimeters a minute. Cycle time was 59 minutes. Then there was a second where we ran it with a 6-flute 3 times the feed rate, 4,500 inches a minute, and it was 26 minutes. So you can see there we've reduced the cycle time by 33 minutes, which is almost a 55.93, 56% reduction in cycle time. Then what we've done is the third one where we used the barrel tool and we used the full 5-axis or 5XC. You'll see we ran twice the feed rate and 3 times the pick rate, and we got the cycle time down to 13 minutes. Well, that's another 13-minute reduction from the middle one there, or another 52%. Or if I look from beginning to end, the total delta was 46 minutes, which means I've taken 78% of the cycle time out of that mold lifter. To take a look at what that means in cost per part, what I've got are the 3 different approaches there, and I'm going to use some prorated rates here. I'm $50 an hour. You can see you're looking at $49.21. Well, on the 5XC, you're looking at right around $11, $10.83. At $100 an hour, almost $100 on the first one, 43. On the last one, you're down to 21. And if you go $150 an hour, you can see 150 to 65 to $32.50. So obviously there is a significant difference in the cost per part. Take that a little further for the mold lifter, and this is the first op that we showed the videos of. Looking at tooling costs, obviously as you go to the second approach and the third approach, the tooling gets more expensive. So you see we've went from $150 to $200 to $250 on the tooling. The tool life we said was going to be 3 hours on the, basically 2-flute ball-nosed end mill. And what we've done, just for comparison sake, is we've kept that the same for the other 2 approaches, even though we know, just because of the approach and the numbers of tool surfaces that you'll be able to use, we know the tool life is going to be better, but we didn't have time during this experiment here to figure out what those tool lives would be. So this is the kind of a worst case scenario where we've assumed the same tool life across the board. Well, if you take and figure out your cost per part, it's almost $50 for op A, it's $29 for the second approach, it's $18 for the third approach. So what you'll see is even though we purchased tooling that was more expensive, 1.67 times the cost per tool, because of the cycle time and the tool life, well, again, we didn't factor in tool life here, we actually saved $31.49, or about a 63.5% reduction in tool life, even though we spent and bought more expensive tooling in order to get the benefits of the 5XC cycle time and surface finishes. On the second group of mold lifter parts, top side, I did the same thing here. You're looking at the first approach, 1,000 millimeters a minute, looking at about 28-minute cycle time. The second one, we got 3 times the feed rate on a 6-flute end mill, so we're 3,000 millimeters a minute. We've gone from 28 minutes to 10-minute cycle time. That's a reduction of 18 minutes, which is 64% cycle time reduction. Well, then the last one, using the barrel cutter, we went 2 times the feed rate and 2 times the pick feed, and we're down to an 8-minute cycle time, so that's an additional 2 minutes or 20% reduction. So if you look at from beginning to end, we've cut 20 minutes or about 71.43, 72% of the cycle time of that part out of the process by going to the 5XC continuous approach to cutting the part, the barrel cam, higher feed rates, higher pick feeds. Doing a similar economic analysis on those three approaches on the mold lifter part, and again at a pro rata rate of about $50 an hour, you can see we ranged at $50 an hour anywhere from about $23 a part down to a $6, $7 a part. At $100, we're looking at $46 all the way down to $13 on the 5XC approach. And at $150, $70 an hour on the initial approach, $25 on the secondary approach. We're down to $20 an hour for that part on the 5XC with the 4 flute and barrel cutter with 2 times the feed rate and 2 times the pick feed. So again, significant financial incentives to take a look at 5XC. I also put together on that second batch of lifter parts, I looked at the tooling costs, and once again, the tooling costs obviously for the second approach and the third approach go up considerably because of the types of tooling and the expense for the tooling. And the tool life, once again, the same argument. We know 3 hours about for the 2 flute ball end mill. So because we didn't have time to actually physically test it, we've used the same 3 hours. There would definitely be a benefit for the second and the third cutters there, the multi-flute and the barrel cutter. So this is a minimum case, if you will. Looking at cost per part, you're looking at anywhere from $23.52 per part to $11.10 to $11.12. So once again, we've got a cost savings here of about $12.40 or about 53% reduction in cost per part, even though we've spent significantly more on the tooling. So that, again, one of the benefits of 5XC. And I would reiterate that we did not take into consideration any extension of tool life as a result of having more cutting surfaces on either the multi-flute ball nose end mill or the multi-flute barrel cutter. We also looked at another part. It's called a center console. This particular would be kind of typical of an automotive application. You can see here the cycle time's about almost 66 hours. This slide is to depict some of the advantages just from the physical geometries that you can achieve with 5XC. Here we've got a center console part, and you'll notice you've got a boss or a radius that's raised down in there, and it's got a 4.5 radius that's 160 millimeters down into the part. Well, right below that, you can see if you were going in there with a traditional 3-axis approach, you have a very large collision potential where you can't get the tool down into the workpiece far enough in order to actually do that machining. To the right there, you can see how we've tilted the spindle and are going down in there with a 5XC approach in order to not only get to the physical feature, but it's also going to allow us to get a better surface finish down in there at that depth. Here's an example of the workpiece set up on the V80S. It's a new machine that Makino's introduced. You can see it has a tilting and rotating spindle, so it allows us to position the tool relative to the workpiece. Here's a little bit more of a zoomed in where we're actually doing 5XC. We're moving all 5 axes simultaneous in order to machine some of the features in this console part. This is a feature down into the part, and you'll notice that the surface that we're machining, there's 2 issues there. Number one, it's sunk below the normal surface of the workpiece, and it's right next to a large boss that sticks up out of the workpiece. So in order to get down in there and get, number one, the reach that we need, and also to get the surfaces blending and matching down in there, this again is one of the advantages, physical advantages of 5XC approach. This is kind of a schematic, if you will, and what we've shown is some areas there where we've went in there with an R1 ball end mill, done 5-axis simultaneous machining. There's also some area back up in the high part of the part where we were in there with a 0.2 end mill and done 5-axis simultaneous machining. Also R4 ball end mill where we're doing 5-axis simultaneous machining. You'll notice some of that's around that boss we talked about earlier, trying to get that back surface and the features that are down into below the surface of the cavity, the core and cavity there. So we're trying to basically go after this part and provide the best surface finishes, blends and matches that we can, obviously for aesthetic purposes, but also we want to make this part as quick as we can for productivity. Here again is one of the advantages. We're looking here at a 0.2 ball end mill, and you'll see on if we were trying to do this with a 3-axis machine, you'll see that we've got a very long extension of the tool in order to get down into some of those surfaces, whereas with 5XC we have the ability to tilt the spindle and get very short, stiff, rigid tooling. That short, stiff, rigid tooling allows us to get down into the very corners and get very good surface finish, very good tool life, very good stiffness and rigidity, which prevents chatter and again enhances the tool life. What I've done here is taken that center console part and put together a bar chart comparing. The top bar there is 30 hours and 32 minutes. Minimum tool radius is an R2. The bottom chart there is doing it on a V80S 5XC approach. And you'll notice we've gone down to 22 hours and 55 minutes with the same R2 ball end mill. So that's about a 25% reduction. Now there's a little red block there on the end, and that's actually another 2 hours and 7 minutes we've added back into the process by going in there with a R.2 ball end mill and doing some finishing on the workpiece. And again, that's for fit, finish, appearance, and also prevent hand working after you take this off the machine tool. So even with the added machining put back in there, we're still down 18% relative to the cycle time it's taken to the 30 hours and 32 minutes it's taken it to do it now. So what I've done here is put together again a comparison. Here's the 3-axis machining, which was 30 hours and 32 minutes. With the same type of ball nose end mill and same type of features and finishes, with the 5XC, we can get down to 22 hours and 55 minutes. The delta is 7 hours and 37. So we've taken a shift, 25% of the cycle time out of that workpiece. However, in order to make a better part, better definition, better blends and matches down into the really small corners, better surface finish, and to prevent hand finishing of this part after it comes off the machine, we added back in a 0.2 ball end mill. Now, keep in mind, in the 3-axis approach, you couldn't even do this because you couldn't get the tool down into some of the areas using the 3-axis approach. It has to be a 5-axis. So, overall summary, even adding back in that machining, the 0.2 ball end mill, we've taken 5 hours and 30 minutes, or 18% out of that part, as compared to the 2 hours and 7 minutes we added back in. So the overall reduction could be 25%. We've gotten down to 18%, but we've got a better part. I've also taken the center console part, and we've went in there and plotted various different X, Y, and Z coordinates, measured them for, as you can see, A, B, C, D, E, F, G features. And you'll notice there that the machining accuracy, even with the 5XC approach, all of it is within 10 micron. So very, very good machining accuracy. Also, looking at the 5XC approach, I wanted to look at surface roughness. The top charts here are 3-axis, the bottom charts are 5-axis, and the little picture there is showing you basically where we're measuring for the different measures. And what you'll notice is if you look at the surface roughness for the 3-axis versus the 5-axis, it's significantly better with the 5XC approach. I've also picked two other areas. Again, you'll see on the top area there, the 3-axis, and the bottom is the 5-axis. And once again, we've done some surface roughness measurements And as you can see, the 5XC approach, or the 5-axis approach, the surface roughness is extremely good compared to the, considerably better than the 3-axis approach. In this particular case, Greg was talking earlier about reducing the time to get into production. So what we've shown here in this slide is based on that center console that we've done, and we've got there a 2+3 or an indexing approach versus a 5-axis. And you'll see on the CAM operations, process design 16 hours versus 6, programming 32 versus 8, numbers of programs 126 versus 46, collision check 32 hours versus 10. So we've overall reduced about 70% of the CAM operation times, and Greg alluded to that earlier. What I've done is went through and kind of shown, here's the 2+3 approach where you've got the process design, the programming, and the collision check. Whereas, so you're looking at 80 hours. Whereas on the 5XC approach, there's your process design, here's your programming, and here's your collision check. So you're looking at about a 24-hour project for that center console versus what was an 80-hour project. So overall, we're looking at about a delta of 56 hours reduction, or about a 70% reduction in the amount of time it takes to design the process, program, and collision check prior to ever even thinking about starting to manufacture a part on the machine. Another thing that, again, Greg alluded to and we showed in the previous slides here, if you look at the number of NC programs, the 2+3 approach would have had 126 programs, versus the 5X approach has 46. So we've reduced the overall number of programs by 80 programs, which is a 63.5% reduction in the numbers of programs, NC programs. Well, Greg, I see we're getting about our time limit here. So what I'd like to do would be go back and do a 5XC continuous summary. We'll talk about the things, try and summarize everything we've talked about. Number one, 5XC can reduce your prep time. We just talked about that here. We showed in the case of that center console where we actually reduced it by 56 hours or 70%. We also talked about 5XC being able to reduce the number of programs. Once again, on the center console, we showed how if we'd have done that with a 2+3 approach or an index approach versus the 5X approach, we went from 126 NC programs to 46. So we reduced the numbers of programs by 80, which is a 63-64% reduction in the overall numbers of programs. The 5XC approach can significantly reduce cutting cycle times. We showed a 78% reduction on the first cut we looked at on the mold lifter and a 71.43 reduction on the second mold lifter that we looked at. So both cases are well over 70%. One's almost 80%. So obviously you can significantly reduce cutting cycle times. We've showed that and demonstrated that on 2 different mold lifter cuts. You can reduce the machining cost per operation. And again, we took a look at those 2 different cuts on the mold lifter. And we went through and looked at the 3 different approaches. The 2-flute end mill, the multi-flute end mill, and then the barrel CAM or barrel cutters. And you can see that there was a significant reduction in the approach, the 5XC approach. Where, just take for example $100 an hour. You're looking at a part traditionally would be $98. With the 5XC approach, we're down to $21.67, and then the second top of the part, $46.67, cut that down to $13.34. So obviously there are significant reductions in the operation cost or cost per piece. We also talked about reducing tooling costs, and this one's kind of really you have to get your head around it, because we're buying more expensive tooling, multi-flute cutters, or the specific barrel type cutters. And we're looking at, as you can see here on the two different mold lifter cuts, we were looking at anywhere from a 52 on the second to a 63. So more than half. We've reduced the tooling cost. Even though we're buying more expensive tooling, we've reduced the tooling cost by more than half, 52.7% on the second mold lifter cut, 63.5% on the first. The other thing to remember with that's while we're purchasing more expensive tooling, and we did not consider any tool life extensions for the multi-flute or the barrel cam type of cutters. And you know they're going to have a better life, so this economics could get even more favorable to the 5XC approach. Talked about reducing cutting cycle times, and again we showed on that center console part where we could have, if we made same part, getting down to the same cutter diameter, we could basically reduce it by 25% on the center console. But we added back in some machining time in order to go in there with a 0.2 ball nose end mill. And the reason we did that, we couldn't even do that on a 3-axis approach because the tool could not get down into the sum of the features. But what that's doing is finishing up and giving us a very pristine, perfect match and blend so that when that part comes off there, we don't have to take it over to a bench and finish it. So even with that, even with adding that machining back in there, we've reduced that part cycle time by 18%, and we've gotten a better part off the machine tool. One of the things we talked about was reducing the total cost per part. And in this particular case, if you remember back, we talked about the honeycomb graphite electrode. We did that part in a 3-axis approach and a 5-axis approach. We're considering, as you can see there, the machining costs and the tooling costs. And actually, we ended up saving almost 23%, 22.8% on the part when you consider the machining cost and the tooling cost by going the 5XC approach versus the 3-axis approach. 5XC also can provide you with a more accurate part. We take a look at the machining accuracy measurements on that center console part, and you can see that entire part, which is a fairly large part. Every position we measured, XYZ, was within plus or minus 10 micron. So the 5XC can produce a more accurate part. In addition, the 5XC can also produce better surface finishes. Once again, if you recall, we talked about the center console part, and we had two different areas where we measured surface roughness, and in 3-axis approach versus 5-axis approach, and the results were that the 5XC approach provides much better, much finer surface finishes. In summary, I think everything we've talked about today are good things for a die and mold manufacturer looking to increase productivity, reduce costs, improve their machining cycle times, improve their quality.